The last chapter has focused on the usage of delay function. If you look at the delay.h file in detail, you will notice that the delay generated by the function is not very accurate. Delay function is implemented as countdown loops with a well-known CPU cycle count per loop iteration. We can use a timer feature of Omega-32 to generate precise delays. If we add interrupt feature to it, we'll free the processor to perform other tasks. Let's see what a timer is. The timers are the facilities built into the AVR that do pulse width modulation, counting external events, delay generation, frequency generation, etc. Imagine an empty bucket of 5-liter size, put under a tap. This tap is dropping 1 drop of water every second. Assume that it takes 4 hours to fill the bucket fully. Now if we keep a half-filled bucket under the same tap, it will take 2 hours to fill the bucket. Timers with any microcontroller works on the same principle of a bucket. Microcontroller speed is decided by the external crystal connected or by the internal oscillator used. We will assume that Omega-32 using internal oscillator of 1 MHz. Omega-32 has a memory area called register name TCNT similar to an empty bucket. The size of TCNT depends on which type of timer you are using. Let's assume we are using timer 0, which can store 8 bits, that is 1 byte value in TCNT. In simple word, for every pulse generated by internal oscillator, TCNT used here will increment by 1. This will increment till its maximum value of 255. 1 byte size memory can store maximum 255 decimal value. As the oscillator is clocking at 1 MHz, indicates that it is generating 1 clock pulse every microsecond. Thus Omega-32 can fill TCNT register in 255 microseconds. This way we can build simple but precise delays using timers. Each type of timer provided by Omega-32 has various modes of operation. We will learn each of them, step by step. We will use timer 0 inches normal mode to generate 1 second delay. Look at the source code. Source code indicate in red color starts the timer 0. Timer 0 can be started by setting 0th bit of TCCR0 register. As we know that timer 0 has an empty bucket type of register named TCNT0. This TCNT0 gets incremented every clock pulse. As the TCNT0 reaches to its highest possible value, the timer overflow flag located under TIFR register sets to high. This indicates that the timer 0 has completed 1 cycle of its operation. Using a while loop, we have monitored the timer overflow flag TOV0. This while loop will end as the TOV0 flag is set to high. Timer 0 will take 255 microseconds to overflow. Thus we have to count overflow for 3921 times to achieve 1 second delay. 3921 times 255 microseconds will result into approximately 1 second delay. TOV0 flag is again cleared by hardware internally and gets ready for the next cycle of overflow. If you observe the code carefully, you will notice that the processor is engaged in monitoring the timer overflow flag and its multiplying factor. We can simplify this application using interrupts in combination with timer 0. This will leave the processor to do some other important task. Also note that this code will not generate a perfect 1 second delay. The source code demonstrates the usage of interrupt and timer together. Interrupt-related code is indicated in blue color. Here we have used a timer 0 overflow interrupt. Due to this, we need not to monitor the timer overflow flag as we have done it in the earlier example. The interrupt handler will blink LEDs connected to port D every second. Now it's time to learn oscillators and crystals used for Omega-32. After learning this, our timer application will become